Water vapor rarely accounts for more than 4% of the atmosphere by volume. In many regions, it is almost non-existent. Yet this small fraction of gas is the primary driver of every major weather event on Earth. This moisture is in a state of constant transit. It moves in a continuous loop between the oceans, the continents, and the air, shifting vast quantities of mass across the globe. The process begins with evaporation. When liquid water absorbs enough thermal energy from its environment, it undergoes a phase change into a gaseous state. This energy is quantified as the latent heat of vaporization. It is the specific amount of heat required to convert a unit of liquid into vapor without increasing its temperature. Essentially, the energy is stored within the vapor itself. Through this continuous cycle of evaporation and transport, the atmosphere functions as a massive system for redistributing thermal energy. It is a continuous exchange of heat and mass, driven by the requirement to reach thermodynamic equilibrium. To understand how the atmosphere manages this moisture, we can isolate a single cubic meter of air. This parcel allows us to track the specific mechanics of humidity. The first metric is absolute humidity. This is the actual weight of water vapor contained within the parcel, expressed in grams per cubic meter. The second metric is relative humidity. This is the percentage of moisture currently present compared to the maximum amount the air could hold at its current temperature. This maximum capacity is not fixed. It is defined by the temperature of the air parcel. When the air temperature increases, its capacity to retain moisture expands. Even if the absolute amount of water stays the same, the relative humidity drops because the parcel is now capable of holding much more. Temperature determines the saturation threshold, dictating exactly when the atmosphere can sustain invisible vapor and when it is forced to release it. Reversing the process, cooling the air parcel shrinks its capacity to hold vapor. As temperature falls, relative humidity climbs. When it reaches 100%, the parcel is saturated, physically incapable of holding additional moisture. We call the temperature at which this occurs the dew point. Cooling beyond the dew point forces the vapor to transform back into liquid through condensation. This phase change is a cooling process for the surrounding air, as it involves the loss of heat. However, in the open atmosphere, water vapor cannot condense spontaneously. It requires a physical surface to act as a catalyst. These catalysts are hygroscopic condensation nuclei, microscopic particles of dust, smoke, or ocean salt. These particles absorb water, allowing vapor molecules to cluster together and form liquid droplets. While thermodynamics create the potential for moisture to leave the air, these microscopic particles are the mechanical requirement that makes weather visible. The forms of condensation seen on the ground are determined by two variables, the location of saturation and the temperature. When the dew point is above freezing, moisture collecting on cool solid objects like grass forms dew. If the dew point is at or below freezing, moisture deposits as minute ice crystals instead of liquid droplets, creating frost. When an entire air mass cools suddenly, moisture condenses onto airborne particles to form fog or mist.
The distinction is density. Fog limits the view to less than 1 kilometer, while mist allows for slightly more. In industrial areas, smoke provides an abundance of these nuclei. Merging with natural fog, it produces the dense, persistent condition known as smog. These phenomena, dew, frost, and fog, are the same physical reaction occurring under different environmental constraints. When condensation occurs at higher elevations, it forms clouds, massive collections of water droplets or ice crystals suspended in free air. At highest altitudes, between 8 and 12,000 meters, are thin, feathery cirrus clouds. Lower down, between 4 and 7,000 meters, are cotton-like cumulus clouds. The lower atmosphere is dominated by layered stratus clouds and dense, dark nimbus clouds. These nimbus formations are so thick they appear opaque, blocking the sun. As condensation continues, these microscopic droplets merge and grow. Eventually, their mass increases to the point where air resistance can no longer support them. If these raindrops fall through a layer of sub-freezing air near the ground, they solidify into small pellets of ice. This is sleet. Hail forms differently. Rainwater is carried vertically through alternating cold layers, accumulating concentric coats of ice before finally falling to the earth. Whether it is rain, or even snow, or falling hail, Precipitation is the moment where accumulated mass finally overcomes the upward force of the air. Since cooling is the prerequisite for rain, the atmosphere requires specific mechanisms to force massive volumes of air to rise and cool. Convectional rain occurs when the surface is heated, causing air to rise in vertical currents. As it ascends, it expands and cools, leading to heavy but brief precipitation. Orographic rain is driven by the landscape. When a saturated air mass hits a mountain, it ascends the windward slope. The forced descent expands the air, dropping its temperature. Condensation results in heavy rainfall on the coastal side. As the air crosses the peak and descends the leeward side, it warms up. Its capacity for moisture increases, but it has already lost its water, creating a dry rain shadow with very little precipitation. Beyond terrain and convection, large-scale cyclonic lifting provides the third major trigger for atmospheric cooling and storm formation. These lifting mechanisms show that geography acts as a mechanical trigger, forcing the phase changes that define regional climates. When we apply these principles globally, distinct patterns emerge. This map shows the distribution of annual rainfall across the planet. The primary trend is a steady decrease in rainfall from the equator toward the poles, following the decline in available solar energy. Proximity to the ocean plays a role. Coasts receive significantly more moisture than continental interiors, which are far from evaporation sources. Prevailing winds refine this map. In mid-latitudes, westerlies slam into western coasts, bringing heavy rain while interiors remain dry. Together, latitude, wind, and terrain create stable regimes. Some regions receive over 200 centimeters of rain annually, while others, trapped in rain shadows or high latitudes, receive less than 50. From a single droplet of dew to a global storm system, these phenomena follow consistent thermodynamic logic. They are the visible evidence of water and heat seeking balance across the atmosphere.